So, I wear many hats. Today I'm going to stack them all on top. I represent a society, Royal Society of Chemistry. RSC has a publishing arm. I'm an e-scientist, so I'm very engaged with how to get science onto the web. I run a chem informatics team, and I'm also an author. I'm going to stack all of those on top of each other and speak from all of those points of view. So I'm writing an article right now because my classical training is as an NMR spectroscopist, and those of you who've ever had an MRI, magnetic resonance was not invented by doctors, it was invented by physicists, stolen by chemists, and then bragged about by doctors. So I'm writing an article here, presently in action with a gentleman at Merck. And when we're writing this, we have a lot of these. This is a figure. It'll end up in a PDF file. It misses all of the true magic of all of the data. I can never rework it. I can never extract from it, because I just have this figure thing going on. But of course, the true magic is buried inside there. And we have lots of those too. Believe me, I don't like to draw those many times. I would much rather, the bottom compound is called vinblastine. I would much rather find that somebody else has drawn properly. I could go to Wikipedia, but now I just have an image again. I actually can't rework it, I can't annotate it very easily because I can't move the bonds and stuff, it's just a figure. So I actually want it in a format that I can do things with. And when I've written all of this, and I've embedded things in Word documents and generated a PDF and handed it over to the publisher, all of the hard work that I will do if my computer ever crashes and I don't use Dropbox for backing up, etc., I will lose all of that. Now imagine that one of you wants to read this article and doesn't want to draw that compound below. How would you grab it? How would you rework it? How would you do 3D optimizations? How would you model it? How would you do things with it? That's the problem we have, is that we put things into formats that don't allow researchers to consume it again in very easy formats. This is an old story, we've heard it many times. I'm not the first one to tell it. Any researcher would say, I wish I could grab things from articles and reuse them much easier. So much of the data that we actually put into an article, we had a great conversation at one of the sit-downs upstairs, is an article is context, story, research data that's been brought together, conclusion, interpretation, referencing, citability. It's got so much value to us. That's not going to go away in the foreseeable future. I'd love to rework the data. A number of times I've reviewed an article and said, well, if I could look into that data, I'd be able to make better conclusions sooner. So we need to try and figure that out, and there's lots of work going on to do that, of course. So the issue with PDF files also is that even if I could try and drag stuff out, it's very confusing to most people what the licensing is. Copyright, what can I do with the content? Data can't be copyrighted. Well, depends who you talk to. There's a lot of confusion around this. But I actually want to get into the data as fast as I can. And then this is a conversation at the bottom that I commonly have. I specialize in X, whatever X may be in any table I sit at. And I want a database of Y's extracted from all of the literature so I can do stuff with the data, so I can model it, so I can report on it, so I can graph it, so I can analyze it, so I can mathematically play with it. And I want the publishers to do it for me for free because they've got all the data, and then I want them to give me all the data and all the tools to do it. So get it done. None of you have ever had that conversation? So the reality of it is that we're making incredible leaps. We should be very proud of how things have shifted just in the past few years. Open access is certainly making all the right moves. Open data, licensing organizations, licensing discussions, the demands for access to the data, these are all becoming much more active. People care a lot more, and they're actionable. The enhanced articles are much easier to read today, especially online HTML articles. There are things that we're doing with them. I'll show you some of our activities. Free online tools, open source code. There's so much stuff out there today. I learned yet again about something I didn't know. Scientists contributing, willingness to do so. I think it is generational, but I also think it is inspirational. There are people who can inspire everybody to get active around things like annotation, I believe. So we should be excited about what's going on, and we have to be very inspirational about what we can do. So this is a typical piece of a publication, right? So we have some graphs there, we have some molecules there, and as a scientist, I'm looking at this paper and I'm reading it, and I see a couple of things that I'd like to query. I want to grab that molecule, I want to find out, has it been patented? Where has it been published before? Who's actually got some sitting on a shelf and can I buy it? How much would it cost me? What has this scientist done in other places? Where's the pharmacology? Which pharmaceutical companies have been working on it? Blah, 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 blah. All of those questions come up. And we go to this thing called Google, commonly, to look for that. The reality of it is that there is work underway to bring all of this together at present. So from the RSC, we sit on 330,000 articles going all the way back to 1841. And we'd love to bring as much of the data that's embedded inside those articles out. They don't go back to the 3rd century, but we do have some people making biblical statements in some of the articles. So what could we do? What do we have the abilities to do today? So we could find chemical names and get structures out of them. There's ways to do that. We could find chemical images and we could get the actual structures in more malleable formats. We'd love to find the reactions, because there's literally hundreds of thousands of reactions sitting inside our articles, just lost. No way to easily find them. We'd love to make a database out of them. We'd like to find all the data that's ever been measured, every melting point, every boiling point, every log P value, every pK value, all these chemical values have been measured that just sit inside these articles. What if we could find all the figures and extract them and database them into more amenable formats for the researcher? Spectra, if you know spectra, I'll show you a couple. I showed you that plot before. But if there are ways to extract spectra today, and I'd love to pull all of them out. There's tens of thousands of them sitting in our electronic supplementary info files, as I call them, dumb figures. Valuable? Dumb. And I'd also validate the data algorithmically, because there are ways that we can do that. So we've been around since 1841, publishing, holding these publications. Of course, we have wonderful resources online now to access the data, and mostly what you're pulling back is the publication itself as an intact format. If you read a publication, and I don't know how many of you can easily see chemicals in that, but it's very simple for a chemist to simply see all the chemistry there. And it's what's written around the chemical terms that tell you, if I mix A with B under these conditions, under these temperatures, using this as a catalyst, then I'm going to get this reaction. And any chemist would be able to draw that conclusion from reading this text. This is easy to do. It's just text mining. Systematic names, so that thing at the bottom is a systematic name for that complex compound. Now, I called it vinblastine before because, believe me, I don't want to read that fancy name at the bottom. It is systematic, it's generated the rules, all the rules are on the right-hand side, highlighted in green, generated by International Union of Pure and Applied Chemistry nomenclature terms. So I can generate systematic names from chemical structures as inputs. I can also do the opposite. Because they're systematic names, I can take those algorithms, I can flip them on their head, with a lot of intelligence, by the way, and now we can get the chemical compound directly out of the systematic name. So if I can find systematic names embedded in my articles, I can pull the chemistry out. Well, here we can see very obvious systematic names. So I can now annotate this with chemical compounds. However, we have a problem. So I'm called Dad, I'm called Social Security number, license number, Orchid ID. I've got many, many names. I've also called other things by other people that are showing their names. But we've all got trivial names, and all chemicals have trivial names too. So they've got cash registry numbers and multilingual names. This is a very simple compound, very, very simple. And if you wanted to search for all incidences of that in patents, that's the list. If you wanted to find every incidence of that compound in free patents online, that's a long list of names, right? So these lookup tables, these synonyms, are very, very difficult to deal with. So we decided to take this on 7 years ago as a hobby project, working from 10 o'clock at night till 2 in the morning, just hacking together online chemistry, trying to integrate as many databases as we could. We produced something called ChemSpider. Many of you hopefully have heard of it. It was acquired by Royal Society of Chemistry 5 years ago, and that's where we reside now. Today, it's 30 million chemicals and growing daily. The data are sourced from 500 data sources. We put our own data in from our articles on a daily basis. We have submissions from the public on a regular basis, crowdsourced curation and annotation. So if you come to one of our 30 million records and you see an error, you have the right to change it, to annotate it, to comment on it. You can change multiple things about it. You can also attach your own data to it. So if you have a compound page on ChemSpider and you want to attach a melting point or a spectral curve, you can do that directly. It's a contribution platform. And it's a structure-centric hub for doing various types of searches, very powerful chemistry-based searches, but it's also a really, really big dictionary. Who cares about a really big dictionary in the world of chemistry? This is what it looks like. Here I've done a search on who wants to say that, right? This is the problem with chemistry. So let's go with Viagra, because we all laugh at it. We all laugh at Viagra, but we all find it. So you want to know about Viagra, you go here. That's not Viagra. Atovaquone. And you find lots of names and identifiers. You find the ways to search across other sources of data online. You find experimental properties, predicted properties. You find literature references. You find ways into patents, all linked up using APIs to Google. You search on a chemical, it will take the list of all of the names associated with that chemical, it will hit the Google Patents API, and it will pull back patents on the fly in real time. We'll also do it against PubMed. We'll also do it against the Google Books interface. We'll also do it against many of the RSC interfaces. And we can just keep plugging in components that are available online. And there's Google Books. And get chemical vendors. So now you have the ability to find out who has this chemical available in their catalog. How much it costs, whether it's in stock is a different question. We don't do that. This is a list of names for aspirin on ChemSpider. Notice that by this third column, you're still stuck in A. My favorite is Xaxa, X-A-X-A is a name for aspirin. It's a headache medicine for Xena, the warrior goddess, I believe. This is an example of taking an article. So on the left-hand side, we see an article where we're hovering over a chemical name. It is a form of annotation where we now show the chemical structure. The chemical structure is coming from the fact that the chemical name is looked up against a big dictionary called ChemSpider, by which point we can link out and see the ChemSpider record. So you go from a name with no actual chemical structure ever supplied with that article out to the database of chemicals with all of its data, all the literature articles linked up, all the patents, all the book articles, etc., etc. So we're text mining the entire archive. We've done all the 21st century articles up to end of 2013. We do it in batches. We have about 100,000 articles already marked up. All marked up with XML, published HTML form online, so you can hardly see the chemistry, etc. It's required multiple iterations, and in fact, we continue to iterate because the dictionary continues to expand. So we can continue to feed the batches through and see if we can find more and more chemistry. To sit and wade through 100,000 articles one at a time and find all the chemical names is a real problem that you don't deal with. We've also got new visualization tools. So this is the latest one. This is a work in progress. This is on MedChem.com, so medicinal chemistry communications. Here we have hide compounds, hide chemical terms, hide biomedical terms, because the articles themselves are shown this way. You can hover over any of these terms and it will give you a link into the definition of what the chemical term is, a link into searching about that chemical. So here's an example. We're hovering over 4,5-difluoro-2-nitroaniline, systematic name, very easy to convert to a chemical structure. You can read more about it on ChemSpider. You can see what the compound is, and ideally, what we'll do ultimately is click, download structure, never draw it again. That's what chemists want to do mostly. We can also query it on something called OpenFacts, which I will get to shortly, and we can predict toxicity by pushing that chemical straight out to a platform, and it predicts toxicity against various algorithms on the fly. They're not already pre-predicted, it's doing it on the fly. And if you imagine the number of APIs that show up online that will now take chemical compounds as feeds, you can generate all of these predictions in real time. So, back to the chemical names, we're already mining compounds, so the question is, in the context now of all of the joins that happen between these chemicals, can we form reactions? A chemist can. Can we do it with text mining? Well, the answer is yes. So we can actually pull reactions now directly out of the text. So we're going to form a database of reactions on the fly being a few weeks of work, some text mining, some pruning, and some crowdsourcing. Fly means a whole different thing now. So is it easy? Well, I'm making it look easy, but of course there's a lot of that going on. And there's a lot of servers in the background, and there's some Hadoop calculations going on, and it's not easy. We've had to put a lot of work in. We're 7 years into the work ourselves. But we depend on ontologies now, and large dictionaries, and some great contributors out in the public domain. So ChemSpider is a compounds repository. We're building a reactions repository, and we will have ways to check the reaction. We'll be able to balance it. We'll be able to see whether or not the product makes any sense to come from the reactants or not. We'll be able to flag it. We'll be able to give it, thank you, we'll be able to give it thumbs up, thumbs head that way, and thumbs down, etc., etc. But why stop at chemicals and reactions? Because science is a whole lot more from the chemistry world. So compounds database is there, reactions database is coming. And this is what I worked with. So this is analytical data, and this is how you get, when you make a mess, which is commonly what shows up in a vial, you want to figure out what it is. So now you run it through lots of instrumentation, and you come out with these lines and peaks and curves, and then you interpret it to end up and confirm what the actual chemical is. Analytical data to chemical compound. That is a lot of value. But most of the electronic supplementary info we host at RSC is all in the form of PDF files and figures. And that is a very valuable piece right there, but I'd like to zoom in on it. In fact, I'd like to reprocess it. I'd like to threshold it, I'd like to pick peaks. I'd like to inverse Fourier transform it, I'd like to apply a new weighting function, I'd like to reprocess it, because I'm that type of guy. I don't have enough TV at home. So here we have at the top, we have the figure directly from the PDF, and at the bottom we have the extracted data. And if your eyes can see a difference, I'll be impressed. The reality of it is there are subtle differences, but in terms of building a database for searching, it's good enough. So if I now go to an instrument, drop in a sample, run a spectrum, hit an API that happens to sit on the RSC's ChemSpider site with the bottom spectrum, I run it on an instrument, and now I hit it onto the web, I'll be able to tell you what the compound is. And imagine if we do that for every spectrum that is sitting inside the RSC database. So we've got some early test experiments, 3,000 pages that we went through for the SI. We found 1,000 instances with spectral data. Got 1,151 spectra out, and 80% of the peaks were extracted to within 1 or 2 decimal places. We're going to do it across the entire archive. And then make it available as a service for anybody to push their own figures into it. We can check data consistency. If we have a spectrum and we have a structure, we'll be able to predict what the spectrum looks like, because there are algorithms that do that, and say, these are incompatible. You might have published saying this spectrum is for that structure, but we're telling you it's not. We already have examples where we're doing that. We can also do the same for things like melting point and boiling point and log p-values. If we have compounds with properties, you can use algorithms to check them. And it's amazing how many errors there are. I personally sat down and I looked. It was 4 years ago I started the project. I looked at every compound on Wikipedia, every atom and every bond, one at a time. And then 6 of us worked for 3 years to clean up the 8% of errors that were sitting on Wikipedia. Every chemical structure on Wikipedia today, we believe, is correct, until somebody goes changes it tomorrow. This is also ESI. So the spectrum at the bottom is how things get described. A list of peaks, a list of positions, a list of coupling constants, a list of shifts. Well, it's possible to extract all of those automatically, and using algorithms, you can now turn those peak positions and coupling constants and intensities into spectra. So even if it's not available as a figure, we can produce a spectral form that looks like that, so we can search against it. And what we'd like to do is carry all the annotations in this case being the assignments. What nuclei on the structure match what peaks in the data. So we're already extracting compounds from compound names, reactions from the text, spectral extraction from figures and text, and ultimately we're going to go through every table that sits in there with a whole list of compounds and a whole list of properties, and we're going to turn them into databases so that we can use that, put it in a database, and in theory build models. But I hate text mining data. I hate it. The fact is we only have that to do because we have an archive going back to 1841. None of us as publishers should ever take in all of this rich data and dumb it down to a PDF file. That's what we shouldn't be doing. We're going to do that for the foreseeable future because we don't have better platforms yet. It's great for an archive. What we should be doing is we should be accepting, demanding data to come in formats that is more reusable. So spectral data in file formats that we can exchange. Compounds that don't come from figures, but actually come in as files that we can manipulate. ESI should be rich and interactive. It should be much better for me to be able to download that and do things with it than depend on people to extract information from what was originally very rich data. So So we're already working to host ESI data that comes in rich file formats on ChemSpider so that it is directly linkable, referenceable out of the article. We can solve it for the authors by telling the authors that we demand that they give us the data in the right formats. I think we're going to hit a big problem, because it can take 2 to 3 years, if not longer, to write up an article, and you ask them the question, please give me that file in the right format, and they'll say, I don't know where it is. My student ran off with it. So we're going to hit a problem there. But we do have researchers who are willing to work with us, so I think we're going to make some progress. So ChemSpider is a foundation platform, however. 30 million chemicals with all of that data sitting in. It's also free for everybody. So anybody in the world can go to it and consume the data. And we also have an API against it. In fact, it's very rich. So when you have an API, you can do wonderful things. So we are part of international consortium agreements, primarily European-based. And I'll just mention a couple. This is Pharmacy. They do know how to spell in Europe. That is S-E-A, because they're finding pharmaceuticals under the sea. Not a sea word. They're dropping big buckets deep into trenches, and they're going to high pressures and high temperatures and low temperatures, sea vents and stuff. And they're trying to find new chemicals. They're already finding new natural products that have never been seen before. And they have evidence that they will find new antibiotics. And if we don't, we're all in trouble. Open facts, they know how to spell facts in Europe. It's pharmacological concept triple store, which is a semantic web project that will generate billions of triples. It meshes together chemistry and biology data, and ChemSpider is dealing with all the chemistry. And it's all open code, open data, open standards, with a very large group involved in the consortium. We're also involved in the open source drug discovery with India to try and discover a cure for TB. We're also involved with building electronic lab notebooks, because ultimately when scientists are generating data, let them put it somewhere that's accessible. Now it can be embargoed, it can be kept private, it can be made public. But of all of the work I've ever done in chemistry, I've only published 5%. 95% of every measurement, every compound I've studied, every measurement I've ever made is gone. And that's a shame. We need to fix that. So we got great progress in mining our archive. Great progress. We will get through it probably in the next 12 months, we hope. Reactions, extraction, and spectral data are underway, and all of the resulting data will be made to the community. And that article I'm writing, ultimately this needs to change. So not only will the article be made available as a PDF file, it will also be generated into a set of nano-publications that should be mineable. The figures will all go up as data ultimately. We'd like all the 2D data to be interactive, downloadable, and reusable. Every one of those compounds will be available for anybody to take, so they never have to draw it again. And how many of you have heard of the INSHI? Please go away and look at Wikipedia for the INSHI, because this is what's connecting the web in terms of chemistry. That compound at the top is vinblastine. You can search on Google for the name vinblastine. That code at the bottom is an INSHI. It's generated directly from the molecule. And if I search that, I find 204 databases online. I just did a chemical structure search of the internet, because we're all starting to use that thing called the International Chemical Identifier. It's one of the best contributions that's come in many years. If you're interested in the slides, they'll be online tonight, and I hope it's been of interest. Thank you.